Hello, my name is Junyoung Park from Yonsei University. Today, I am going to talk about layer-wise auto-weighting for non-stationary test-time adaptation. Most pre-trained deep neural networks perform well in a single domain but struggle in situations involving domain shift. This phenomenon compromises the overall generalizability and robustness of neural knowledge. Therefore, various approaches have been developed to enhance plasticity in target domain knowledge, including domain adaptation and domain generalization. In contrast to domain adaptation, which utilizes the source domain dataset, test-time adaptation solely relies on target dataset without labels in adaptation process. Given the prevalence of changing domains in the real world, recent efforts have been directed towards addressing the challenges posed by non-stationary domains in test-time adaptation. In a deep neural network, different levels of feature maps represent different types of information from the input. Therefore, the best performance after adaptation on different domain distributions can be achieved by selectively tuning distinct layers. However, previous test-time adaptation approaches have not demonstrated these properties. As a result, we propose a novel layer-wise auto-weighting algorithm that autonomously identifies the layers requiring knowledge preservation or plasticity on a target domain. Our approach does not rely on any source-related information and optimizes the network with a simpler framework and lower computational load. We make an algorithm that identifies the importance and defines the step size for each layer. This reduces the need for empirical search when tuning layers in various domain shift situations, ensuring greater robustness across multiple domain shifts. At each time step, test time batch samples serve as inputs to the model. The augmented input, denoted as X set, serves as hard target samples, assuming easier target samples output Y as an anchor for prediction in consistency loss. With gradient from negative log likelihood loss, we can calculate score function of each layer. With the score function from each layer, we can obtain a Fisher information matrix that approximates the Hessian with lower computational complexity. We then accumulate the Fisher information matrix at each time step to obtain a domain-level Fisher information matrix. The traces of the layer's Fisher information matrix serve as approximations of the curvatures, indicating the sharpness in distribution variances. We define these traces as layer-wise importance values and normalize them using an exponential min-max scalar to mitigate unstable learning caused by the outliers. The objective for test-time adaptation includes entropy minimization loss and consistency loss. Utilizing the layer-wise learning rate defined above, all parameters are optimized with different step sizes. This enables the separation of the importance of each learnable parameter embedded in each layer, facilitating optimization with domain-specific step sizes. We've conducted experiments on 3 representative corruption benchmark datasets: Cypher 10C, Cypher 100C, and ImageNet-C. For non-stationary test time adaptation settings, we performed continual test time adaptation, which assumes sequentially changing domain distributions without model resetting, and gradual test time adaptation, which assumes sequentially increasing or decreasing domain distributions without a model resetting process. Our method outperforms manual freezing of DNA layers, as you can see from the left figure, and also it maintains a reasonable computational load while demonstrating superior performance compared to other approaches, as you can see from the right figure. These are the online average classification errors for continual test time adaptation. Our method demonstrates comparable performance and maintains a lower computational load, even though our approach is entirely inaccessible to source information. And these are the online average classification errors for gradual test time adaptation. Therefore, our method demonstrates comparable performance in both non-stationary test time adaptation scenarios for classification. All ablation results were conducted on continual test time adaptation. Our method exhibits better performance than the previous approaches for layer-wise fine-tuning. Even without the consistency loss, which addresses miscalibration problems, layer-wise optimization shows superior results across all datasets. We also conducted ablation on the hyperparameter of the exponential min-max scalar for each dataset. This is the end of my presentation, and thank you for listening. Find more details and experimental results on our paper and code implementation.